Hmm. So in the last episode, we discussed it till the question number 45. So coming to question number 46. So as the load is increased, the speed of the DC shunt motor. Okay. So if you write the voltage equation of the DC shunt motor, we know that V equal to E plus IARA, right? So E equal to V minus IARA. So E I can write as KFI into omega equal to V minus IARA. So omega equal to V by KFI minus IARA into, or IARA divided by K into 5. If suppose IA equal to 0, so omega equal to V by KFI. If IA is increasing, means this term will increase, right? So VA by KFI minus something. So omega will decrease, right? So it will be reduces slightly. Coming to question number 47. So in the question it is given shaft shunt compound generator. So let me make the diagram. So this is shunt field and this is series field, okay? And this is the voltage. So the voltage is given as 250 volt, and it is given the load current is of 100 amp, and this is the DC generator, okay? And they had given the shunt field winding is 130 ohm, and they had given armature resistance is 0.1 ohm, and series field is also 0.1 ohm, okay? So they had given the brush drop is 1 volt, okay? Brush drop is 1 volt for each brush, okay? For each brush. So there are two brushes. So total drop will be 2 volt, okay? So they ask the EMF generated. So they want easy, okay? Easy. So in order to calculate this easy, we will use the basic network analysis. So if you write the loop equation here, okay? So easy equal to 250 plus IARA. IA is the armature current. This is the IA. Okay. So IARA plus IA plus 100. Sorry. IARA into, sorry, IARA plus 100 into 0.1. So this is the drop. 100 into 0.1. Okay. Plus 2 volt. This is the brush drop. Okay. So easy equal to 250 plus 10 plus 2, that is equal to 262 plus IA into RA is 0.1. So if you know the IA value, you can calculate easy. So for that we will do one more thing. So if you apply the loop analysis here, okay, so then you can write easy equal to IARA plus brush drop of 2 volts plus IA minus 100 into 130, right? So this is IARA plus 2 volt plus 130 IA minus 13000. Okay. So now if you what we will do, equation 1 and equation 2. So both will be equal, right? So what I will do equal to 260 plus 0.1 IA equal to 0.1 IA plus 2 volt plus 130 IA minus 13,000. Okay. So this will be cancelled. So 13 and 262 minus 2. So it will be 13 260 equal to 130 into IA. Okay. So 13 1 is 13, 13 2 is 26. So IA equal to 102 ampere. Okay. 102. So substitute this in equation 1. So E is equal to 262 plus 102 into 0.1. So So that equal to 10.2. It will be 10.2. So answer will be 272.2 volt. Okay. Answer will be here. Coming to question number 48. Okay. So the leakage flux in a transformer. Generally, you know that in a transformer, if you consider a winding, primary winding, okay, if you supply with the voltage V, so the flux will develop. This flux links with the secondary winding, and the EMF is induced here. Okay, but some part of flux will leak through air, right? Because okay, will leak through air. So why? Because air is also provide path for the flux, provide path for the flux. So that means air is not a magnetic insulator. Okay, air is not a magnetic insulator. So that's why answer is okay. Okay. Coming to question number 14, the no load input power to a transformer is practically equal to. So the no load is that is like open circuit test, right? In open circuit test, what are the losses we will observe? Only iron losses because the copper losses in the no load loss equal to I square into R, right? So this current is very less because of no load, right? So this losses will be negligible. So the only loss is iron loss. Okay. Coming to question number 50. So the torque versus armature current graph of DC series motor. If you see the torque is proportional to phi into Ia, right? In series motor, phi is proportional to Ia because the field winding and armature winding both are in series, right? In series winding, these both are in series. So flux is directly proportional to armature current. So torque is directly proportional to armature current square. But if you think at some point of time, this flux will be saturated. Okay. So once the flux is saturated, torque is directly proportional to only Ia. So for some time, it follows the parabolic path because it is proportional to Ia square. After that, it follows linear. This is the linear and this is the parabolic path. So answer will be uh, parabola up to full load and straight line at overload. Okay, at overload because at higher armature currents, flux will be saturated. Okay, so that's the answer will be B. Okay. Coming to question number 51. So this question is already discussed in episode 1. Okay, episode 1. The same question it is repeated. Answer will be 3 to 5%. Okay. Coming to question number 52. So it is given 100% efficient transformer. So the primary winding is 1000 turns and secondary is 100 turns. Okay. So if the power input to the above transformer is 100 watt, so they had given input power. Okay, 1000 watts. So they asked the power output. So if you see the device, it is transformer. So transformer is a constant power device. So answer will be the same, 1000 watts. Okay, and it is also given that it is 100% efficient. Okay. Okay. So what is the efficiency of the transformer compared with the electric motors? So generally motors are the rotating type devices, right? So they had rotational losses also. But if you consider the transformer, it is a static device. So there will be no rotational losses. So transformer is having higher efficiency. Okay. So it is having higher efficiency compared to the electrical motors. Okay. Okay. Coming to question number 54, I make a diagram of a DC generator. Okay. And this is north and this is south pole. So the current is indicated in the armature. Okay. So now if you make the flux direction like this, right, by the thumb rule, and this will be like this. Not here, it will be linked with this also. I mean, this both. So if you observe this, the direction of the flux, it will be from right to left, right? So If I cancel this flux, actually this is the armature flux, right? So this is the responsible for the armature reaction. If I cancel this, then I can reduce the armature reaction. So in order to cancel this, we can introduce the flux in the opposite direction of the same amount. Okay, so we can reduce the armature reaction. For that, what we will do is we usually put conductors here in the armature pole here, which is of opposite direction. Why? Because in order to reduce the armature flux, so it will provide a flux which is opposite to the this flux. Okay, so it will be in this direction. So both will be cancelled out, and the armature flux will be reduced. But the flux along the interpolar axis, right? Some part of the flux like this also, right? But this flux cannot be reduced by the compensating winding. Why? Because this compensating winding is provided in the pole faces, so it will constrain to the pole arc only, right? So this region it will be confined. So the MMF provided by the compensating winding is equal to pole arc by pole pitch into MMF provided by the armature winding per pole. Okay, so this factor is always less than 1. Okay, so MMF is, you can write N into I compensating winding, right? So N of compensating winding. So the N is tens here. Okay, so we can write that Z of compensating winding, okay, that is conductors, is less than Z of armature conductors. Why? Because the compensating winding is only confined to the pole arc region only. It cannot compensate the armature flux in the interpolar axis. Okay, so that's why this factor will come, pole arc by pole pitch. It will be less than 1. So that's why the number of conductors in the compensating winding is always less than the number of conductors in the armature. Okay, answer will be B. Okay, so coming to question number 55. In a DC machine, how the commutating pole winding is connected. Okay. So generally, commutating pole is also called as interpole. Okay. So interpole usually use it to compensate the flux in the interpolar region. Okay, interpolar region. So what we will do in interpole region, the armature flux is this, suppose. So what we will do, we will create an opposite flux which is of the same amount like armature flux in the opposite direction to nullify that effect. Okay. So in order to provide the same amount of flux, we need to connect this in series, right? Because the same amount of armature current we needed. So we always connect in series with the armature winding. Okay. And this also, and compensating winding also will connect in the series also. Coming to question number 56. So actually the break test for determination of efficiency. Okay. Generally in the testing of DC machines, there are two tests. Okay. So one is direct testing and other is indirect testing. So direct testing is for small rating missions. This is for high rating missions. Okay. So in this indirect testing, there are two testings like Swinburne test, and Hopkinson Hopkinson test. Okay. So direct test is for in this brake test. Okay. So they asked the brake test. Okay. So brake test is generally used for small rating mission. So this is an indirect test, right? Or direct test. Tell me. So it is not an indirect test. So it is a direct test. Okay. So coming to question number 57. Okay. So commutation at full load, a large DC machine can be checked by. So first thing is they given that large machine. Okay. So if you see high rating machine, I already said it is in under test. In high rating, Swinburne and Hopkinson test is used. So brake test is eliminated. So out of B and C, one option is right. So the thing is they said that the full load. Okay. So generally Swinburne test, this is for no load test. And this is for full load. And you can say at any load, we can calculate that, the stray load losses. So Hopkinson test is the right answer. Hmm. Coming to question number 59. In a DC motor, starters are used too. Okay. So generally at starting speed equal to zero, right? So we can write IA, armature current equal to V minus E by RA, right? So we know E is proportional to phi into omega. As omega equal to 0, E is 0. So this is 0. So V by RA. Okay, V by RA. So actually V minus E drop is less, right? Because V minus V is denoting the drop, right? So generally it will be less. But if E is 0, this term will be high. So the armature current will be high. So at starting, there will be high current. There will be high current. So in order to reduce this, what we will do at the starting, we will increase the armature resistance by providing a external resistance. So if you increase the denominator, then the armature current will be reduced. So the starters are only provided to limit the starting current. Okay, not to increase the starting current. So answer will be B. Okay. Coming to question number 60. So the voltage regulation of a transformer having copper loss. So generally percentage copper loss is equal to percentage R. Okay. So it is given as 1%. So percentage X is given as 5%. And the cos phi power factor is given as 0.9. So they ask the voltage regulation. The voltage regulation is direct formula, percentage cos phi plus or minus, okay, percentage X into sin phi R. Okay. So generally plus for lagging, minus for leading. So voltage regulation equal to percentage R we know 1 into cos phi R we know 0.9 plus percentage X is 5 into sin phi R. Okay. So this you can calculate by calculator only. Okay. Let me tell you how we can get. This is phi. Okay. Cos phi equal to I can write 9 by 10, right? So 9 is adjacent, 10 is hypotenuse. Okay. Now if you want to calculate this portion, so which is equal to 10 square minus 9 square under root, right? So it will be around 19. So it will be greater than 4. So that I assume greater than 4 only. So sin phi equal to greater than 4 divided by 10. So it will be greater than 0.4 something. Okay. So substitute in here. Voltage regulation equal to 0.9 plus 5 into greater than 0.4. So 0.9 plus 4 5 is 20, right? So it will be 2. So it will be greater than 2. So 2.9. So greater than 2.9. So answer will be 3.08. Okay. So you can do this question by approximation only. Okay. So we cannot calculate the sin phi value, exact value, because we don't have calculator, right? Okay. So coming to 61%. Okay. So a 4-pole lamp mount DC generator has the following details. Okay. Flux per pole is given as 0.07 and speed is given as 900 rpm. So armature conductors is given as 440. Okay, they had given 4-pole mission and it is lap one. Okay, in lap one, armature poles equal to number of parallel paths. Okay, number of parallel paths and this is poles. So we know generated EMF formula Zn P5 by 60 into A. So as A and P are equal, both will be cancelled. So Z equal to 440. This is not volts, sorry. 440 into 900 into 0.07 divided by 60. Okay, if you calculate this, like you can write this as 9 into 7. Okay, because 0.07 you can write as 7 by 100. Okay, so 3 3 is a 9, 320, uh, 22. So 66 into 7. Okay, so 42 and 462. Okay, answer will be C. Okay, so coming to question number 62, the maximum power delivered in the DC generator. Okay, so power equal to EC into IA, right? So EC into IA you can write as EC minus V by RA, right? So in order to get maximum power, what we will do? Differentiation equal to 0, right? So if you do the differentiation, 2 EC by RA minus V by RA equal to 0. So 2 is equal to V. So E is equal to V by 2. So as you know that V is supply voltage, so answer will be E. Okay. So the DC motor having the high starting torque. Okay. So in general, you know that torque is directly proportional to phi into Ia, right? So in series motor, flux is directly proportional to Ia. So torque is directly proportional to Ia square. So in DC series motor, the torque is square of the armature current. So it will provide high starting torque. So answer will be series motor. Okay. So DC generator commutator acts as a, you know that this is already discussed. It came around 2 to 3 times. So answer will be B. Okay. If the AC supply to a if the AC supply to a transformer is replaced by the DC, like suppose question number 65. Okay. So this is a transformer and the winding is here. Okay. Now you provide the supply voltage V and EMF is induced here. Okay. So you know that E is proportional to E is equal to E equal to N d5 by dt. Now if you give the supply as constant DC supply, so flux will be constant. So E equal to N into d by dt of some constant F. So differentiation of the constant is 0. So E equal to 0. So this will be shorted. So high amount of current will flow through the primary winding and the primary winding will be burned. Okay. Coming to secondary winding, if the EMF induced in the primary is 0, secondary is also 0. Secondary is also 0. It is connected with a load R, right? Okay. Now if you observe, primary winding has source voltage V and it is shorted. And secondary winding is 0 volt and shorted. Okay. So if anything is shorted with a source, then it will result into high current. But here there is no source. Okay. So there is no current to drive that circuit. Okay. So the secondary winding will not burn, but the primary winding will burn. Okay. So coming to question number 66. So they given that DC shunt generator is there, an external resistance is connected, okay, in series with the field circuit. So when external resistance is connected, the total resistance will increase, right? So field current will decrease. So flux will decrease, right? So we know that E equal to Ka phi into omega, right? So if we consider DC generator speed is given by prime mover, right? Speed will be given by prime mover. It is as input. So if we consider this as constant, so E is proportional to phi, right? As field flux is decreasing, E also decrease. So which in turn decrease the terminal voltage, right? So answer will be the decrease in the voltage of the generator. Okay. Okay. So coming to 67th question. This is like the same as case as the above question. But here field flux in general what we do is field flux control. We connected external resistance in series with the field winding. Okay. Like the above case. So resistance will increase, right? So field current will decrease, right? So field flux will decrease. But here they had given that motor. So in motor, input is what? Voltage. So let me assume input as constant. So E equal to Ka into omega, right? So this is constant. So phi is inversely proportional to 1 by speed. So phi is decreasing, so omega will increase. So speed is higher than the rated speed. Okay. So the above question is the same concept as below question, but above question is regarding the DC generator. So below question is regarding the DC motor. Okay. Okay. So coming to question number 68. What will happen if the supply terminals of a shunt motor is interchanged? Okay. So this is supply. Okay. And this is shunt motor. So armature current will be like this. Field current will be like this. Now what they did is they interchanged the supply like minus and this is plus. Now the armature current direction will be like this and field current direction will be like this, right? So we know that torque is proportional to phi into Ia, right? So in general, phi is proportional to field current If into Ia. So here, if you observe the current direction in both cases, in the first case, Ia is from top to bottom and ISH is also top to bottom. But in the second case, both Ia and ISH are reversed. So if IF is negative and Ia also negative, so multiplication will be positive, right? So there will be no effect on electromagnetic torque. Okay, so the speed will be same as previous. There is no change in the rotation. Okay, so motor will run it as normal in the same direction, because here both are changing. Okay, if any one of the thing is changed, like if the armature current is direction only changed, or if the field current direction only changed, then the motor will run in the opposite direction to the original condition. Okay, so coming to question number 69. Okay, a transformer has a core loss of 64 watt. Okay, 1 minute. Okay, so copper loss is given as 144 watt when it is carrying 120% overload current, means it is given at 1.2 times of IFR. Okay, at this load, these two conditions given. So x square copper loss. Okay, x square copper loss at full load equal to copper loss at that particular load. We know this, right? So x is given as 1.2 square into copper loss at full load. At this load, it is given as 144. So copper loss at full load equal to 144 by 1.44. So which is equal to 100 watt. So copper loss at full load, we got that 100 watt. So what they ask is the load at which transformer will operate at maximum efficiency. So the load at which they operate at maximum efficiency X is equal to root over P core loss by P copper loss at flow. So that equal to P core loss is 64, which is constant. So it will not change, and divided by 100. So answer would be 8 by 10, which is equal to 80%. 80% of the load. So answer will be A. Okay. Uh, Two transformers operating in parallel will share the load depending upon their this depending upon their which parameters per unit impedance and ratings also and ratings. So answer will be ratings. Okay. This is direct parallel operation of the transformer. Direct question. Okay. Okay. So which of the following transformer is smallest? Okay. So in order to calculate this, we have to see the kVA by frequency. This will give the information of the specific weight of the transformer. So if this ratio, okay, if this ratio is more, then the weight of the transformer is more. That means it is the large transformer. So if you calculate the first option, 1 by 50, and this is 1 by 200, C is 1 by 400, and D is 1 by 600. So out of the four options, this 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 ratio is the smallest, right? So this is the small rating transformer, smallest transformer, because this has specific weight less specific weight. Okay. Okay. Coming to question number 72. Okay. Short circuit test. Okay. Generally, open circuit test is for core loss, and short circuit test is for copper loss. Okay. So answer will be copper loss. Hmm. So question number 73. Under heavy loads, the transformer efficiency is comparatively low. You know that efficiency is dependent on output by output plus loss. So loss is copper loss plus iron loss, right? So if you see copper loss is dependent on current, right? Load current. So if load current is more, then copper loss will be more. So this denominator will be more. So the efficiency will decrease, right? So the answer will be copper loss becomes high in proportion to the output.